got two presentations in the next session. And yeah, we'll pass you over to,
Dounia Hammou.
Dounia. Perfect. So, ColorVideoVDP.
ML, the new version. So, hello everyone. So, my name is Dounia Hammou, and I'm finally a PhD student at the University of Cambridge under the supervision of Rafal Mantouk. And as he said, we're presenting today ColorVideoVDP-ML. So, this is, as you can guess, a new variant of ColorVideoVDP with a neural regressor for image and video quality prediction. So for anyone here who doesn't know about ColorVideoVDP yet, so ColorVideoVDP is a metric that is based on psychophysical model of the human visual system, basically to assess the visibility of distortion between a test and a reference video, and that can be either as a quality score, histogram, or distortion map. So because it's based on psychophysical model, so it can account for display specification, making it basically make it able to work with SDR and HDR content on every display and viewing condition. Also, another thing is that it's a white box model based on low-level human vision with only very few learnable parameters. We only have 33, which allow it more or less to be generalizable across a diverse range of distortion. However, the main issue with ColorVideoVDP is that it's only based on low-level human vision, so it doesn't really account for high-level vision. So, for instance, here we're showing the distortion map of ColorVideoVDP, and you can kind of see that it's assigning similar importance to the background and to the foreground. And in reality, most people, if they're watching a TV like this, they're mostly focusing on the foreground and discarding the distortion that's happening in the background. And another problematic case in ColorVideoVDP is that it penalizes per pixel differences in high entropy textures. For instance, when you have leaves or like, for example, the curly hair on this person here. So it's going to like give them high distortion, and most people will actually not be able to distinguish these per pixel differences. So the idea here is that we came with this new variant. We still want to use the low-level human visuals of ColorVideoVDP, but we want to also employ a neural regressor for higher-level visual processing. So this is more or less like the overview of the framework, and here I'm going to be delving onto each block of this framework. So starting with the backbone, or just like a brief overview of ColorVideoVDP. So ColorVideoVDP will be taken as any metric, the test video and the reference video, and what distinguishes it really is the display model. So basically, it's going to take all this information about the color space, resolution, viewing distance, the luminance of the display, the ambient light, because it basically operates on the physical unit of the luminance. So what happens is that it's going to transfer our image to exactly the light that has been emitted from the display at this specific display and viewing condition. So in kind of more details, what it does is that transform our input to the decayal color space. So you have the luminance, red, green, and yellow, violet, and these two are mostly to like account for chromatic distortion. And it also have a temporal decomposition. Basically, we get a transient channel, which gives us information about like fast motion. Here, the video is kind of still, so you cannot really see much information in the transient channel. So basically, when it got all the information for the different channels, it's going to decompose our whatever channel with a multi-scale decomposition, specifically the Laplacian pyramid. And so basically, we're going to get different bands at different spatial frequency. And this basically allows us to encode the contrast and measure its visibility using the CSF, which requires the spatial frequency of your band. And it does that again for the different channels, and we get at the end like the test contrast, the different band for the test contrast and the reference contrast. Again, then apply contrast masking to get the perceptual difference. So I'm not going into a lot of detail because this is more a ColorVideoVDP part, but how ColorVideoVDP works is that it takes this perceptual difference information and then pull them to a quality score, which is why it doesn't really account for this kind of semantic information. So here what we're taking is not only the perceptual difference, but we also want to take the test contrast information and the reference contrast information to be able to get from them some semantic information about the importance of a region in an image or a video. So as a small summary, so for each video and for each different channel, we're going to get our different band for the test contrast, reference contrast, and the perceptual difference. And basically to reduce the size of this, the size of our features, we're going to take like non-overlapping patches. Each patch is the number of pixels per 1 visual degree. And we take only 2 statistics from each patch. So we take only the mean and the standard deviation. This kind of gives us at the end 24 features. So we have 2 statistics, 4 different channels, and we have the test, reference, contrast, and the perceptual difference giving us 24 features for each patch, for each different band at different spatial frequency, and for each frame. So this step of reducing or like the feature pooling is basically going to help us to reduce the size of our extracted feature from like terabyte to gigabyte, which will make basically the training just way more efficient. So now to the most important part is the regression network. So here we want to have like a regression network that tries to learn from this kind of feature some kind of high-level visual processing. So we tried 2 simple architecture, one using MLP and one using a transformer. So we start with the first architecture, which we call ColorVideoVDP-ML saliency. Here the idea is that we're using MLP as a predictor, and we have 2 types of predictors. We have a distortion predictor, and we have a saliency predictor. So the distortion predictor is just going to take this perceptual difference features and try to get one score that represents how much amount of distortion appear in this patch. And then we use the reference contrast features and a test contrast feature to get some information about saliency, how important is that region that will be used to weigh the distortion prediction. And then at the end, we'll have one quality score per each patch, band, and frame, which we're going to average across all of them to get the final quality score for our video. So here, we are not, for example, we're not training the saliency predictor on eye tracking data or anything like this. The idea was to train everything on a quality data set and to see how to learn some kind of saliency that's more related to the context of quality metrics. So one issue with this kind of architecture is that it only takes one single patch feature as an input, which means it cannot really learn different relationship between the different patches in a spatial context. The second idea is to use, obviously, a transformer, so which we call ColorVideoVDP-ML transformer. So the idea here is that we're going to have all our patches, and then we're going to give them to a transformer encoder to learn this kind of relationship between the different patches. So when we have all our different patches, we first encode them in MLP. We're actually using only one linear layer, just because our features are already given from ColorVideoVDP, so they already have in meaningful units, so we didn't need to like do more processing on them. And then we add a learnable token, CLC, and we give it to our transformer. And then using the MLP, we get a final quality score across each band and each frame, and then we average across all of them again to get the quality score per video. So there are 2 things you can notice in this architecture, is that first, we don't have positional encoding. Interestingly, is that we actually tried the positional encoding and didn't really improve the performance at all. It gave very similar results, so which is why we kind of omitted it here. We honestly don't know why. It's something that just happened when we tried it. And the second thing is that we're only learning relationship between patches. We're not learning relationship between band and frame. Just in the scope of the project, and because of complexity, we wanted to not learn all the different relationships. So we focus only on the patches. One thing is that we may not really need information across bands just because they are all in similar units, but probably like the relationship between the frames may be something like more interesting to learn, for example, when you have temporal distortions. So for training our, basically our quality metric, we use 4 different datasets. So we have HDR, SDR, VQA dataset, UPIC, Lab HDR, and XR-David. So we have a collection of HDR, SDR images and videos with very different like distortion. So we have streaming distortion, we have display distortion, and the only reason we were able to actually train on multiple datasets is that all of them were scaled in GOD units, which make it basically they have consistent quality across the different kind of quality datasets. And we also tested on obviously the test part of each of the training dataset, but also on other datasets like HDR-VDC, Lab VQA, Lab Mobile, and CADID. So besides HDR-VDC, the others have like most kind of scores, and HDR-VDC has GOD scores. So for example, the reason we choose this data for the training is that UPIC, Lab HDR, XR-David, which actually ColorVideoVDP is trained on, they are like more typical kind of datasets in which when you see them is that all region have the same kind, like all region matter in the frame. So usually when you're watching them, you're focusing on mostly all parts of the image or your frame. However, the issue with HDR SDR VQA dataset, or the reason we actually add it, and is because it has like obvious objects or like silent objects. So as you can see here in this image, mostly the people will be focusing on the silent object or the foreground and basically discarding the background. And this is one data. So for example, when we saw that ColorVideoVDP was doing incredibly bad on it. So even after fine tuning it on this dataset, it did not work. So let's look at how our ColorVideoVDP-ML perform. So here, as a beginning, we're showing the results only for HDR, SDR, VQA dataset because it has been like a really challenging dataset. And we're showing here the correlation scores. So one thing you can notice is that ColorVideoVDP-ML, both variants actually perform just so much better than ColorVideoVDP on this challenging dataset, just because ColorVideoVDP doesn't have any kind of semantic information, so it could not perform well on it. However, when we kind of looked overall, so across different datasets, one thing we noticed that ColorVideoVDP-ML transformer do perform better than ColorVideoVDP for the HDR, SDR, VQA dataset. It also performed better on UPIC, so we found that UPIC had some benefit of using this semantic information. However, if you look for live HDR, for example, XR-David and the other dataset, the performance was actually very similar. And that's because, again, as I showed you in the previous image or the previous slide, in those cases, you don't really need information about like the semantic information. So that's why the performance didn't really change that much. ColorVideoVDP-ML silency, on the other hand, showed some kind of overfitting, so it didn't really generalize well for other unseen data. And that's probably just because its architecture is very simple, which led it to have like very big like overfitting compared to like ColorVideoVDP-ML transformer. So then we also wanted to compare ColorVideoVDP-ML transformer with other metric. So we actually compared it with many other metrics, but here we're showing just like topic, VMAF, LPIPS, which are like one of the most interesting one that we found it have interesting results. So topic is an image quality metric, which also have like transformer architecture, and it actually does so well on many datasets. So as you can see for topic, it also did so well on this HDR, SDR, VQA dataset that has been challenging because it has this kind of a transformer architecture and it can lean the silent regions. It also did very well on many other datasets. It only showed like it kinda didn't generalize well for live VQA and XR-David, which have some kind of display distortion. So in that case, ColorVideoVDP-ML transformer did better than it in a significant way. On the other hand, VMAF, which I know everyone knows about it, so it does very well on any kind of streaming, distortion dataset. So it did very well on many of the datasets, but it didn't do, for example, so well on HDR, SDR, VQA datasets, which again, because VMAF doesn't also like account for this kind of semantic information, but also didn't do well on XR-David, and that kind of expected just because this one has display distortion, which are kind of unknown to VMAF. And then LPIPS, we added it because we found it interesting that it actually didn't perform well on most of the datasets. We were expecting like better performance usually because it's used quite a lot, but we kind of show that many, like our metric at least, is either doing similarly to some metrics or better than like more challenging datasets. Okay, so to look more into how well ColorVideoVDP-ML does. So here we're looking more into the distortion visibility heat map. So for our test image, here I trained ColorVideoVDP-ML, but without any information from the test and reference contrast filter. So I just had like an MLP that take the differences and predict the quality at the end. And the same as showed you in the beginning of the presentation, you can kind of see that ColorVideoVDP-ML without any semantic information is penalizing the background in the same manner as it does for the foreground, and it doesn't learn any of this information. ColorVideoVDP-ML silency, on the other hand, you can kind of see that it's penalized less now the background and focus mostly on the foreground, but it still accounts for some distortion in the background. The ColorVideoVDP-ML transformer, on the other hand, barely accounts for anything in the background and focus mostly on the foreground, and also, for example, doesn't penalize a lot for like distortion that are in high entropy kind of textures, which is actually what we were looking for in our metric. So this kind of shows that ColorVideoVDP-ML transformer is behaving more or less what we expect from an observer, is like focusing basically on the foreground and not noticing much differences in high texture, like high entropy textures. So so far we kind of looked at ColorVDP-ML performance in terms of correlation and in a qualitative way. Another question we wanted to also ask ourselves is that now we added a machine learning component to ColorVDP. So is it still modeling CSF accurately? So this was a bit harder question to ask. So to do that, basically we generated synthetic test images. So we have different images that show Gabor patches, different contrast level, and at different spatial frequency. So this kind of data is the same data that's usually used to collect CSF from observer. And then for each of the images, we run the quality metric, and we got the prediction. So we have the prediction as control plot for different contrast and different spatial frequency. And the idea is that a metric that's able to model CSF accurately will be able to follow the behavior of CSF across spatial frequencies. And here we have some kind of alignment code that show how well it follow this red curve. And here we're comparing ColorVDP. As you can expect, ColorVDP is able, because it doesn't have any kind of learnable component, is able to follow more accurately the CSF. However, ColorVDP-ML saliency, you can see it's kind of following for very low contrast, but then it shows these weird islands. And it's some kind of effect that we've seen in a lot of deep learning metric, is that they're doing very bad on these areas. And ColorVideoVDP-ML transformer does even worse. It shows even more Iceland, even weirder kind of islands, meaning that if I want to use ColorVideoVDP-ML transformer, I will not be able to reliably say that it'll be able to account well, for example, the impact of viewing distance, because it doesn't really follow the CSF very accurately compared to ColorVideoVDP, even if it has higher correlation coefficients. Another question we wanted to also ask ourselves is that can ColorVideoVDP-ML use as a loss function? So here we did a very kind of simple test, is that we took 4 images from TID 2013, and then we compressed them with JPEG from quality 0 to 100. And then just run the quality metrics on them, and we got the prediction. So idea here is that if a metric can be used as a loss function, it should first be monotonic, meaning the gradient shouldn't go below 0, and also the gradient should be smooth, which we kind of see here in ColorVideoVDP. ColorVideoVDP-ML also showed smooth gradient. However, it showed that it was slightly non-monotonic at the beginning. And as you've seen in the beginning, how terrible the quality is, you can imagine that ColorVideoVDP-ML just didn't see this terrible distortion like this. So it couldn't really learn this kind of things. So if you imagine that you start in your training from something very random, it actually may never converge because it will always stop at this local minima. And then ColorVideoVDP-ML transformer showed even worse results. It showed that actually the gradient was not smooth at all, but it was actually non-monotonic as well. So if you use it as a loss function, you will always end in a lot of local minimas. And also you have this weird behavior that at very high quality scores, it's actually decreased. And this kind of behavior, we didn't only see it with ColorVideoVDP-ML. I don't have the graphs here, but we also seen it with Topic, which is also based on transformer. We also seen it with AHEC, the same weird kind of variation in gradient and the non-monotonic behavior. So we believe this is part of the transformer. So even if transformer usually are going to give you very high quality scores, they may actually struggle with other things. So for example, modeling CSF here or having monotonic prediction. So in conclusion, here in this work, we present a ColorVideoVDP-ML. So it's basically shown that psychophysical model of the human visual system can be combined with machine learning models, which improve the ability to generalize, allow us to account for SD and AGR content, which is usually the hardest bit. And then it also accounts for viewing condition. And this ML head basically potentially allow us to learn high-level vision, so example, saliency and texture similarity. And we found that using large training datasets was really helpful throughout the training and the generalization. And that was only possible because the different datasets had the same GOD scaling. However, we also found that the machine learning component impact negatively both the modeling of the CSF and the monotonicity of the prediction. It's still a work in progress. It's still something that we're still working on and trying to improve. We still want to have the same high correlation that we get using transformer, but we want to also be able to model accurately the CSF and all the viewing condition, display condition, and have something that can be used as a loss function. So that's all for my part. So if you need more information, there is a project webpage, and you can also access the code. It's available. And honestly, I would be grateful if anyone tried this on their different benchmarks. And I would like more feedback on the metric for us to be able to improve more on it. Thank you very much.
Simon?
Yeah. So I will ask two questions. You can answer them at the same time. So by the way, I'm the biggest fan of ColorVideoVDP, so thank you for your work. So first question is, when you're using them as a loss function, you have temporal decomposition, spatial decomposition. How was temporal decomposition part differentiable when you're using them as a loss function?
So how is it? I think it's built in a way that everything is differentiable within. I don't know how Rafal did the temporal decomposition. That's part of ColorVideoVDP, right?
Yeah. You have temporal decomposition in the ColorVideoVDP backbone, right?
Yeah.
So that part is differentiable?
Yes.
Okay. So the second question is, ColorVideoVDP working a window over 250 milliseconds, that is around 10 frames of, let's say, 30 FPS. So that's a lot of computation to do when you're using a loss function. Would that be a very slow function to use when you train the models? Or?
Unfortunately, yes. If you are using it directly for training like a big model, it will probably be quite slow.
Okay. Yeah. Thanks.
So I understand CVVDP is a proper human visual system model, and you can rely on this. So it can be explainable and so on. Now, adding this ML thingy to after the front end, and especially looking at the data related to contrast sensitivity function and monotonicity, it looks like it will properly give better scores on some data sets, but it becomes unpredictable.
Yes.
You know, the consistency of the scores, or can you rely on this? Because, yeah, you probably have a lot of data sets to train this on, but if you use some different data sets, in the standard version, you can be confident that the scores will somehow correlate to what people will say, because it is a proper human visual system model. Now you add a component which is unpredictable. You don't know. It is black box.
Yes.
So is it? Do you think of something that can be made into to follow really CSF, to be monotonic, or to have more insight into what ML is in fact doing? Because having one scores on 5 data sets, it does not really mean on the 6th or the 7th data set, it will be still consistent.
Yes, that's why we added like the extra test to like verify how well it does. And we actually did, as you can see, found that it doesn't really do well. Again, it's something we're also looking into. I personally will not fully rely on ColorVideoVDP-ML at the moment. We can understand ColorVideoVDP. We believe we tried this on other data set. We saw this data set, and it generalized on most of the data set that have content or distortion that are similar to existing one. So it's not like it will not generalize like VMAF or other topic or other learnable kind of metrics. But will it be able to perform well and everything? We cannot say this yet, because as you see in this machine learning part, it's become a black box, and it's actually affect also the behavior of CSF and ColorVideoVDP backbone. So it's again something we're trying to fix or work more on. So we still want to have something that follows CSF regardless, but still be able to add this kind of semantic information that we have better understanding of. But it's a work in progress, unfortunately.
Okay, thank you.
Yeah, thank you for the talk. I kind of have a similar question to that. I mean, so I'll ask you a question, then I'll ask a follow-up question. How did you train the ML model? What loss function did you use for that?
So we use MSE.
And I wonder, you know how we're always going on that Pearson R and SSIM are not good metrics, right? Is it because maybe that the model was trained with the wrong metrics? I know it's a bit of a chicken and egg problem, right? We don't have the right loss functions to use to train these models. But I wonder if you could use some regularization term like ColorVideoVDP or like a CSF bias metric to enforce those perceptual characteristics on the model.
That's actually a very good idea. So yeah, the reason we use MSE is because we knew that the GOD scores between the different data sets are similar. So we believe that even if you use MSE, it's probably going to learn something similar. We are also thinking of using Pearson, so something to learn more of a distribution rather than to just have these fixed scores that follow exactly the MSE. I think the idea of regularization to make it like follow CSF is a good idea. I can only say that I will definitely try this.
Oh no, I always wonder, obviously with these learning-based models,
Yes.
is they're not probably going to learn perceptual-based models, are they? They're going to learn kind of automatic stuff that doesn't rely on human vision.
Yeah.
So sometimes enforcing human visual characteristics in the loss functions can be a good idea sometimes.
Yeah, that's a good idea. I'll definitely try this.
Cool.
Thank you.
Thank you. Any more? Okay. Thank you very much.
Thank you.